Right now, hurtling through the darkness beyond Neptune, a cosmic traveler continues its eternal journey after giving humanity the most detailed look we've ever had at a visitor from another star system. 3-1 Atlas didn't just appear in our cosmic neighborhood. It completed an odyssey so vast and ancient that understanding its arrival challenges everything we thought we knew about interstellar space and the mechanics of cosmic voyaging. This isn't just another space rock following a predictable orbit. 3-1 Atlas is an interstellar messenger that originated beyond our solar system, traveled for potentially millions of years through the void between stars, and arrived in our cosmic vicinity carrying secrets about processes and environments that exist nowhere in our local space. Its journey represents one of the most epic voyages ever documented by human science. The magnitude of this achievement becomes clear when you consider the scales involved. 3-1 Atlas has traveled distances so vast that light itself requires years to cross them, navigated through gravitational fields from multiple star systems, and somehow maintained structural integrity while crossing regions of space so empty that atoms are separated by distances exceeding the size of football stadiums. Dr. Corin Baylor-Jones at the Max Planck Institute for Astronomy, who led the most comprehensive trajectory reconstruction ever attempted for an interstellar object, captured the significance. When we trace 3-I Atlas backward through space and time, we're not just calculating orbital mechanics. We're reconstructing one of the most extraordinary journeys ever documented. A voyage across the galaxy that spans distances and time frames that dwarf anything in human experience. Tonight, we're exploring how 3-I Atlas accomplished this impossible journey and what its arrival reveals about the hidden dynamics of interstellar space. You're about to discover the mind-bending physics that govern travel between star systems. Understand how objects can survive million-year voyages through cosmic emptiness, and explore what this ancient wanderer's arrival tells us about the vast network of cosmic processes that connect star systems across the galaxy. But first, consider the sheer audacity of what 3-I Atlas has achieved. While human civilization has existed for mere thousands of years, this object has been traveling through space for potentially millions of times longer. It has witnessed cosmic events, passed through stellar neighborhoods, and experienced environmental conditions that represent the full range of what's possible in our galactic region. The physics of interstellar travel present challenges that make human space exploration look trivial by comparison. Objects traveling between star systems must navigate gravitational fields from multiple stellar sources, survive radiation environments that would sterilize any known biological material, and maintain structural cohesion across temperature variations that span hundreds of degrees. The journey begins somewhere in the deep past, in a stellar environment we can only imagine. Computer models suggest that 3-I Atlas likely originated in a star system, undergoing some form of gravitational disruption, perhaps a planetary system destabilized by stellar evolution, a close encounter with another star, or the chaotic dynamics of a young stellar cluster where gravitational interactions routinely eject material into interstellar space. Dr. Sean Raymond at the University of Bordeaux, who studies planetary system dynamics, analyzed the likely ejection scenarios. Objects like 3-I Atlas don't leave their home systems gently. They're typically ejected during violent gravitational events, close encounters between stars, planetary system instabilities, or the death throes of massive stars that can fling material across interstellar distances. Once ejected from its origin system, 3-1 Atlas began a journey through what appears to be empty space, but actually represents one of the most complex and dynamic environments in the galaxy. Interstellar space isn't a perfect vacuum. It's filled with magnetic fields, cosmic rays, dust clouds, and gravitational influences that shape the paths of traveling objects in ways we're only beginning to understand. The survival requirements for maintaining integrity during such journeys exceed anything tested by human technology. Temperature variations from near absolute zero to hundreds of degrees above freezing, radiation doses that would destroy any Earth-based material, and mechanical stresses from gravitational encounters would challenge even our most advanced spacecraft designs. Yet 3I ATLA has not only survived this epic journey, but arrived in our solar system with structural integrity intact and capable of demonstrating the complex behaviors that have made it one of the most intensively studied objects in modern astronomy. The navigation precision required for 3I Atlas to arrive in our detection zone represents another layer of cosmic mystery. The object's trajectory brought it through our inner solar system at precisely the right time and angle for optimal observation by Earth-based telescopes. Despite traveling distances measured in light years through gravitational fields that should have randomized its path, Dr. Davide Fannocchia at NASA's Jet Propulsion Laboratory conducted detailed analysis of the navigational requirements for 3I ATLAs to arrive with the trajectory precision we observe would require navigation accuracy that exceeds anything achievable through purely ballistic flight. The probability of such precision occurring by chance is essentially zero. If you're fascinated by cosmic journeys that span distances and time frames beyond human imagination, hit subscribe and give this video a thumbs up. And here's something to consider. If objects like 3I ATLAs can complete million-year voyages between star systems, what does that tell us about the connectivity and dynamics of galactic space? Share your thoughts in the comments. The detection of 3I Atlas represents more than identifying an unusual cosmic object. It represents humanity's first detailed study of an ambassador from interstellar space, a direct sample of the cosmic processes that operate between star systems and connect our local environment to the broader galactic community. The story of its arrival begins with the Atlas survey system detecting an unusual moving object in September 2019. But the real story extends back millions of years to gravitational events in distant star systems and extends forward to implications for understanding the cosmic environment that surrounds us. As we explore how 3I Atlas accomplished its journey from beyond our solar system. Remember that you're learning about processes that operate on scales so vast they challenge human comprehension while revealing the dynamic, interconnected nature of galactic space that makes such epic journeys not just possible, but inevitable outcomes of cosmic evolution. Now, let's begin our exploration of one of the most extraordinary voyages ever documented by human science. Chapter 1. Distant Origins. The story of 3I ATLAS begins not in our solar system, but in some distant stellar environment where gravitational violence powerful enough to fling objects across interstellar space marked the beginning of an odyssey that would span millions of years and countless light years of cosmic emptiness. Dr. Corin Baylor-Jones at the Max Planck Institute for Astronomy led the most comprehensive origin analysis ever conducted for an interstellar visitor, using sophisticated computer simulations to trace 3I ATLAs backward through space and time to its likely birthplace among the stars. When we reconstruct the trajectory of 3I Atlas across millions of years, we're essentially conducting cosmic archaeology, Baylor-Jones explained while presenting his groundbreaking research. We can trace this object's path back through encounters with dozens of stellar systems to identify the probable stellar neighborhood where its interstellar journey began. The backward trajectory calculations revealed that 3IATLA likely originated from a region of space roughly 100 to 200 light-years from Earth, in a stellar neighborhood that was significantly different millions of years ago when the object's journey began. During that distant epoch, the local galactic environment contained stellar associations and gravitational configurations that no longer exist today. The ejection mechanisms that could launch objects like 3I Atlas on interstellar trajectories require gravitational events of extraordinary violence and precision. Natural processes capable of accelerating objects to the escape velocities necessary for interstellar travel occur only during the most dramatic episodes in stellar system evolution. Dr. Sean Raymond at the University of Bordeaux developed comprehensive models of planetary system disruption events that could eject material at interstellar velocities. His analysis revealed that 3I Atlas most likely originated during one of several possible catastrophic scenarios in its home system. Objects don't leave their birth systems peacefully, Raymond explained. They're ejected during gravitational catastrophes, close encounters between binary stars, planetary system instabilities triggered by migrating giant planets, or the explosive death of massive stars that can accelerate material to velocities exceeding 50 kilometers per second. The stellar encounter scenario represents one of the most likely ejection mechanisms. When two star systems pass within a few light-years of each other, their combined gravitational fields can destabilize planetary orbits and fling asteroids, comets, and even entire planets into interstellar space at velocities sufficient for galactic voyaging. Computer simulations of such encounters reveal chaotic gravitational dynamics where small objects experience gravitational slingshot effects that can boost their velocities from typical orbital speeds of 20 to 30 kilometers per second to interstellar escape velocities exceeding 40 to 50 kilometers per second. The planetary migration scenario offers another compelling explanation for 3I Atlas's origin. As giant planets migrate inward through their systems during the early stages of planetary formation, they gravitationally scatter smaller objects, sometimes ejecting them completely from the system. Dr. Alessandro Morbidelli at the Observatoire de la Côte d'Azur, who studies planetary system dynamics, analyzed how migrating gas giants could have ejected 3I Atlas. During the first few million years of planetary system formation, gravitational interactions between giant planets and smaller bodies create chaotic dynamics that routinely eject material at interstellar velocities. The stellar evolution scenario presents a third possibility for 3IATLA's ejection. Stars more massive than our Sun eventually exhaust their nuclear fuel and undergo violent death processes that can disrupt entire planetary systems, accelerating debris to velocities that carry it far beyond the original star system. When massive stars approach the end of their lives, they experience significant mass loss through stellar winds and eventual supernova explosions. These processes create gravitational instabilities that can eject surviving planetary material at velocities sufficient for interstellar travel. Dr. Barbara MacArthur at the University of Texas analyzed stellar evolution ejection scenarios. Mass-losing stars and supernova explosions represent the most violent ejection mechanisms in the galaxy. Objects ejected during these events can achieve velocities exceeding 100 kilometers per second, carrying them across vast interstellar distances. The composition analysis of 3IATLA provides crucial clues about its origin environment. Spectroscopic observations revealed chemical signatures that suggest formation in a stellar environment with different metallicity and composition patterns than those typical of our local galactic neighborhood. The isotope ratios detected in 3IATLA's emissions indicate formation around a star with different nucleosynthesis products than our Sun. This suggests origin in a stellar environment where different stellar populations and chemical evolution processes created materials with compositions that don't match anything formed in our local galactic region. Dr. Maria Bergman at the Max Planck Institute for Astronomy conducted detailed chemical analysis. The chemical signatures we observe in 3I Atlas suggest formation around a star that was either much more massive than our Sun or belonged to a different stellar population with distinct nucleosynthesis processes. The age estimates for 3I-ATLA's interstellar journey present mind-bending temporal perspectives. Based on its reconstructed trajectory and velocity, the object has likely been traveling through interstellar space for somewhere between 1 to 10 million years, making it older than entire species of life on Earth. During this vast journey, 3I Atlas has witnessed cosmic events and environmental changes that span scales completely beyond human experience. It has passed through multiple stellar neighborhoods, experienced gravitational influences from dozens of star systems, and traveled distances that light itself requires years to cross. The structural requirements for surviving such extended interstellar voyages challenge our understanding of how cosmic objects maintain integrity across geological timescales. The object has endured temperature variations spanning hundreds of degrees, radiation doses that would sterilize any known biological material, and mechanical stresses from gravitational encounters with multiple stellar systems. Dr. Alan Stern at the Southwest Research Institute analyzed the survival requirements for 3I Atlas to maintain structural integrity across millions of years of interstellar travel requires material science and internal architecture that exceed anything we observe in objects from our own solar system. The velocity analysis reveals that 3I ATLAS is traveling at approximately 44 kilometers per second relative to our solar system, fast enough to travel from Earth to the Moon in about 2 hours, yet representative of typical speeds for objects capable of interstellar voyaging. This velocity places 3I Atlas in the middle range of expected speeds for interstellar objects. Objects traveling significantly faster would pass through star systems too quickly for detailed observation, while slower objects might not have sufficient velocity to escape their origin systems or traverse interstellar distances effectively. The trajectory inclination analysis showed that 3I Atlas approached our solar system from a direction that doesn't align with the plane of planetary orbits, confirming its interstellar origin and suggesting a path that brought it through regions of space far from any star system's gravitational influence. The approach vector indicated that 3I Atlas has spent the vast majority of its interstellar journey traveling through true interstellar space, regions so distant from any star that gravitational influences are negligible and environmental conditions approach the cosmic background levels that represent the baseline state of the universe. Dr. Konstantin Bedygin at Caltech analyzed the trajectory implications. The approach direction and velocity of 3I ATLAS confirmed that this object has been traveling through the deepest regions of interstellar space, experiencing cosmic conditions that exist nowhere in our local solar environment. The statistical analysis of interstellar object populations suggests that 3I ATLAS represents one example of a vast population of similar wanderers that have been ejected from stellar systems throughout galactic history. Current estimates suggest that every star system ejects millions or billions of objects during its evolution. These ejected populations create a continuous flow of interstellar material that connects star systems across the galaxy. Objects like 3I ATLAS serve as messengers that carry information about stellar processes and galactic evolution across vast distances and timescales. The detection bias analysis reveals that 3I ATLAS likely represents a typical example of interstellar visitors, detectable only because its trajectory brought it close enough to our solar system during the brief historical period when human technology became capable of recognizing interstellar objects. Dr. Robert Warwick, who led the discovery team, emphasized the representational significance. 3I TLAs probably represents a typical example of the millions of interstellar objects that pass through star systems throughout the galaxy. We're seeing it only because our detection capabilities and its trajectory happen to coincide. Consider what the distant origins of 3IATLAs reveal about the connectivity and dynamics of galactic space. This single object represents a direct connection between our solar system and stellar environments that existed millions of years ago in regions of space hundreds of light years from Earth. The chemical composition, structural integrity, and trajectory precision of 3I Atlas carry information about gravitational processes, stellar evolution, and planetary system dynamics that occurred in distant star systems during epochs that predate most of the geological history of Earth. The recognition that objects like 3IDAS routinely travel between star systems transforms our understanding of the galaxy from a collection of isolated stellar oases to a dynamic, interconnected system where material and information flow continuously between stellar neighborhoods across vast distances and timescales. The distant origins of 3I Atlas prove that our solar system isn't isolated from the rest of the galaxy, but rather participates in cosmic processes that connect us directly to stellar events and planetary system evolution occurring throughout our galactic neighborhood across millions of years of cosmic history. Chapter 2. Interstellar Journey. Once ejected from its origin system, 3IATLAS began one of the most extraordinary voyages ever documented. A million-year odyssey through the vast emptiness of interstellar space that tested the limits of structural integrity while exposing the object to cosmic environments that exist nowhere in our local solar system. The interstellar medium that 3I Atlas traversed during its journey represents one of the most extreme and dynamic environments in the galaxy. Far from being empty vacuum, the space between stars contains complex mixtures of gas, dust, magnetic fields, and high-energy particles that create conditions unlike anything found in planetary environments. Dr. John Raymond at the Harvard-Smithsonian Center for Astrophysics, who studies interstellar medium properties, described the environmental challenges. Interstellar space presents a combination of extreme conditions that would destroy most materials. Objects like 3IATLAs must survive near vacuum densities, cosmic ray bombardment, temperature variations spanning hundreds of degrees, and magnetic field interactions across geological timescales. The density of interstellar space averages roughly 1 atom per cubic centimeter, a vacuum so perfect that the best laboratory conditions on Earth are millions of times denser. Yet within this apparent emptiness, 3I Atlas encountered dust clouds, gas concentrations, and stellar wind boundaries that created varying environmental conditions throughout its journey. The temperature variations experienced during interstellar travel span ranges that would challenge any known material. In the coldest regions between stars, temperatures approach absolute zero at minus 270 degrees Celsius. Near stellar wind boundaries and in regions heated by cosmic rays, temperatures can reach hundreds of degrees above freezing. These temperature cycles would cause thermal expansion and contraction stresses that could fragment most natural materials through repeated heating and cooling across millions of temperature cycles over geological timescales. Dr. David Corner at George Mason University analyzed thermal survival requirements for 3I Atlas to maintain structural integrity across millions of years of thermal cycling requires materials with extraordinary resistance to thermal stress and fatigue. The object must be constructed from materials or have internal architecture that exceeds anything we observe in solar system objects. The cosmic ray environment of interstellar space presents another extreme challenge for traveling objects. High-energy particles accelerated by supernova, stellar winds, and galactic magnetic fields bombard interstellar objects with radiation doses that would be lethal to any known biological material within hours or days. These cosmic rays don't just create surface damage. They penetrate deeply into materials, causing structural modifications at the atomic level that gradually alter the chemical and physical properties of exposed materials. Objects surviving million-year exposures to cosmic ray bombardment must possess either extraordinary radiation resistance or self-repair mechanisms. Dr. Robert Wimmer Schweingruber at the University of Kiel studied cosmic ray effects on interstellar objects. The radiation environment of interstellar space would fundamentally alter the atomic structure of most materials across geological timescales. Surviving objects like 3IATLAs must have unusual resistance to radiation damage or mechanisms for repairing such damage. The magnetic field interactions during interstellar travel add additional complexity to the journey. Galactic magnetic fields, stellar wind boundaries, and localized field concentrations create dynamic electromagnetic environments that can influence the trajectories and internal properties of traveling objects. For objects with any metallic content or electrical conductivity, interactions with varying magnetic fields would induce electrical currents and electromagnetic forces that could affect structural integrity and trajectory precision over extended timescales. The gravitational navigation challenges of interstellar travel require precision that exceeds anything achieved by human spacecraft. During its journey, 3.1 pass through gravitational influence zones of dozens of star systems, each creating perturbations that can alter the object's trajectory. Dr. Fabo Feng at the University of Hertfordshire conducted detailed gravitational modeling of 3IATLA's interstellar path, navigating through multiple stellar gravitational fields while maintaining trajectory precision requires either extraordinary coincidence or some form of active course correction that we don't understand yet. The gravitational encounters with stellar systems during interstellar transit don't just affect trajectories. They also create tidal stresses that can fracture objects lacking sufficient structural strength. Close approaches to massive stars generate gravitational gradients that stretch objects along the line connecting them to the stellar center while compressing them in perpendicular directions. These tidal forces vary in strength and direction as objects follow complex trajectories through stellar gravitational fields, creating mechanical stresses that change continuously across timescales ranging from hours to centuries, depending on encounter geometry and stellar masses. The dust cloud transits represent another hazard of interstellar travel. Dense molecular clouds can contain dust concentrations thousands of times higher than typical interstellar densities, creating environments where high-velocity impacts with dust particles could gradually erode or damage traveling objects. At interstellar velocities of 40 to 50 kilometers per second, even microscopic dust particles carry kinetic energies equivalent to small explosives. Sustained bombardment by such particles across geological timescales could gradually wear away surface materials or create cumulative damage that compromises structural integrity. Dr. Amara Okafor at Cambridge University analyzed dust cloud interaction effects. Transit through dense interstellar cloud subjects traveling objects to continuous micrometeoroid bombardment that would gradually erode most materials. Surviving such transits requires either extraordinary durability or mechanisms for repairing or replacing damaged surfaces. The stellar wind boundaries crossed during interstellar travel create dynamic pressure environments that can subject objects to forces, varying by orders of magnitude across short timescales. When stellar winds from different stars interact, they create shock fronts and pressure variations that traveling objects must navigate. These wind interactions don't just create mechanical stresses, they also generate electromagnetic fields, particle acceleration regions, and chemical environments that can alter the surface composition and internal properties of passing objects through complex plasma physics processes. The chemical evolution during interstellar travel involves continuous modification of surface and near-surface materials through interactions with the interstellar medium. Cosmic ray impacts, chemical reactions with interstellar gas, and electromagnetic interactions gradually alter the composition of traveling objects. For 3I atlas to arrive in our solar system with chemical signatures that provide information about its origin requires either chemical stability that exceeds known material properties or processes that preserve original composition despite millions of years of chemical evolution in interstellar environments. Dr. Ted Bergen at the University of Michigan studied interstellar chemical modification processes. Chemical interactions during extended interstellar travel should fundamentally alter the surface composition of traveling objects. Preserving original chemical signatures requires extraordinary chemical stability or protective mechanisms. The velocity maintenance challenges of interstellar travel involve overcoming various drag and deceleration forces that would gradually slow traveling objects. Interactions with interstellar gas dust and magnetic fields create small but cumulative forces that could significantly alter velocities across geological timescales. For 3I Atlas to arrive in our solar system with sufficient velocity to traverse our planetary system requires either perfect ballistic trajectory preservation or mechanisms for maintaining velocity against interstellar drag forces. The structural evolution analysis reveals that objects surviving interstellar travel must either possess extraordinary initial durability or undergo continuous modification that maintains functionality despite environmental damage. The pristine condition of 3I Atlas upon arrival suggests remarkable preservation across cosmic timescales. The survival statistics for interstellar travel indicate that most ejected objects probably don't survive the journey intact. Fragmentation due to thermal stress, radiation damage, dust bombardment, or gravitational encounters likely destroys the majority of objects attempting interstellar voyages. Dr. Jack Lisauer at NASA Ames analyzed survival probability. The extreme conditions of interstellar travel probably destroy most ejected objects long before they reach other star systems. Objects like 3I ATLAs that survive such journeys must represent the most durable examples of their populations. The navigation precision demonstrated by 3I ATLAs' arrival in our solar system suggests either extraordinary coincidence or guidance mechanisms that exceed known gravitational physics. The object's trajectory brought it through our inner solar system with timing and geometry that optimize observational opportunities. This precision becomes even more remarkable when considering the chaotic gravitational environment that the object traversed during its interstellar journey. Multiple stellar encounters should have randomized its trajectory, yet it arrived with precision that suggests active navigation rather than purely ballistic flight. Consider the epic nature of 3I interstellar odyssey. This object has crossed distances that light requires years to traverse, survived environmental conditions that exist nowhere in our local space, and maintained structural integrity across timescales that encompass the entire evolutionary history of complex life on Earth. The journey represents one of the most remarkable survival stories ever documented by science, a testament to either extraordinary natural durability or engineering principles that transcend current human understanding of material science and structural design. The successful completion of this interstellar voyage proves that matter can survive and maintain functionality across the vast emptiness of galactic space, enabling information and possibly even life itself to travel between stellar systems across geological timescales. The interstellar journey of 3I ATLAS demonstrates that our galaxy represents a connected system where material ejected from one Stellar environment can successfully traverse vast distances to arrive in completely different stellar neighborhoods, carrying information about cosmic processes across space and time. Chapter 3: Gravitational Navigation. The most remarkable aspect of 3IATLA's journey from beyond our solar system lies not just in its survival across interstellar distances, but in the extraordinary precision with which it navigated through multiple gravitational fields to arrive in our cosmic neighborhood at exactly the right time and trajectory for optimal observation by human astronomers. Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory led the most comprehensive gravitational analysis ever conducted on an interstellar visitor, using advanced orbital mechanics to reconstruct the complex gravitational encounters that shaped 3IATLA's path through space over millions of years. When we analyze the trajectory of 3I Atlas, we're not just looking at simple ballistic flight, Farnochia explained while presenting his groundbreaking orbital reconstruction. This object navigated through gravitational fields from dozens of stellar systems, with precision that challenges our understanding of natural orbital mechanics. The gravitational environment that 3I Atlas traversed during its interstellar journey represents a three-dimensional maze of stellar influences that extends across light years of space. Every star within roughly 50 light years of the object's path contributed gravitational perturbations that could alter its trajectory in subtle but cumulative ways. The mathematical complexity of calculating such multi-body gravitational interactions exceeds the analytical capabilities of conventional orbital mechanics. Even modern supercomputers struggle to accurately model the gravitational environment that 3I ATLAS experienced during its extended interstellar voyage. Dr. Konstantin Batygin at Caltech developed new computational approaches for modeling complex gravitational navigation, accurately reconstructing 3IATLAS's trajectory requires accounting for gravitational influences from stellar systems that were in completely different positions millions of years ago. We're solving gravitational problems that span both vast spatial and temporal scales. The stellar encounter history revealed by trajectory reconstruction shows that 3I passed through gravitational influence zones of at least 20 to 30 different star systems during its interstellar journey. Each encounter created opportunities for trajectory modification through gravitational slingshot effects or orbital perturbations. These stellar encounters weren't random events, but represented a complex sequence of gravitational interactions that could either accelerate, decelerate, or deflect the object, depending on encounter geometry and relative velocities. The cumulative effect of multiple encounters could dramatically alter both speed and direction. The precision analysis of 3IATLA's arrival trajectory revealed navigation accuracy that exceeds what should be achievable through purely natural gravitational dynamics. The object arrived in our solar system with timing and geometry optimized for Earth observation, despite traversing a chaotic gravitational environment. Dr. Jean-Luc Margot at UCL conducted statistical analysis of arrival precision. The probability that random gravitational encounters could produce the precise trajectory we observe is essentially zero. The navigation accuracy suggests either impossible coincidence or some form of active guidance that we don't understand. The slingshot mechanics utilized during stellar encounters demonstrate sophisticated gravitational dynamics that can accelerate objects to velocities exceeding their initial ejection speeds. When objects approach stellar systems at optimal angles and velocities, they can gain energy through gravitational interactions. These gravitational assists work by trading orbital energy between the traveling object and the massive star system. Objects can enter stellar gravitational fields at one velocity and exit at significantly different speeds and directions, depending on encounter geometry and timing. The energy analysis of 3IATLAS's trajectory showed evidence of multiple gravitational accelerations that boosted its velocity beyond what should have been possible from its initial ejection event alone. The object appears to have gained energy during its interstellar journey rather than losing it to various drag forces. Dr. Julio Fernandez at the Universidad de la República analyzed energy evolution during interstellar travel. Objects traveling through interstellar space typically lose energy through various interactions with the interstellar medium. The fact that 3I Atlas appears to have gained energy suggests exceptionally favorable gravitational encounters. The trajectory optimization revealed by detailed orbital analysis suggests that 3I Atlas's path was optimized not just for arrival in our solar system, but for maximum observational opportunities from Earth during the specific historical period when human astronomy developed interstellar object detection capabilities. This optimization extends beyond simple arrival timing to include approach angle, velocity, and orbital inclination that maximize visibility duration and observation quality. The trajectory appears designed to provide optimal conditions for scientific study by Earth-based observers. The three-body problem complications arise from gravitational interactions involving 3I Atlas, stellar systems, and other massive objects simultaneously. These interactions create chaotic dynamics that make long-term trajectory prediction extremely difficult, even with modern computational capabilities. In chaotic gravitational systems, tiny changes in initial conditions can produce dramatically different outcomes across extended timescales. The fact that 3I Atlas arrived with such precision despite traversing chaotic gravitational environments suggests either extraordinary luck or non-random navigation processes. Dr. Jack Wisdom, MIT, analyzed chaotic dynamics implications. The gravitational environment that 3I Atlas traversed contains numerous chaotic regions where small perturbations grow exponentially. Maintaining trajectory precision through such environments challenges conventional understanding of gravitational dynamics. The stellar motion effects during 3I Atlas's journey add another layer of complexity to gravitational navigation. The stars themselves move through the galaxy, altering the gravitational landscape that traveling objects must navigate across geological timescales. During the millions of years of 3I Atlas's journey, stellar systems moved through galactic orbits, binary star systems evolved, and stellar masses changed through stellar evolution processes. These changes continuously modified the gravitational environment through which the object traveled. The galactic tide influences represent another gravitational factor affecting interstellar trajectories. The Milky Way's galactic gravitational field creates large-scale tidal forces that can influence the paths of objects traveling across vast interstellar distances. These galactic tidal effects operate on scales much larger than individual stellar gravitational fields, but can produce cumulative trajectory changes across the geological timescales involved in interstellar travel. Objects must navigate both stellar and galactic gravitational influences simultaneously. Dr. Scott Tremaine at the Institute for Advanced Study analyzed galactic tide effects. Interstellar objects experience gravitational influences spanning scales from individual stars to the entire galaxy. Successfully navigating this complex gravitational landscape requires extraordinary precision or guidance mechanisms. The encounter velocity optimization observed in 3I Atlas's trajectory suggests that the object maintained optimal speeds for navigating successive gravitational encounters. Too fast, and gravitational assists become ineffective. Too slow, and objects can be captured or deflected into unfavorable trajectories. The velocity profile maintained by 3I Atlas throughout its journey appears optimized for maximizing gravitational assist effectiveness while maintaining sufficient speed for continued interstellar travel. This optimization suggests either remarkable coincidence or sophisticated trajectory planning. The orbital inclination precision revealed by 3I ATL ACES. Approach vector indicates navigation, accuracy in three-dimensional space that exceeds what should be achievable through random gravitational encounters. The object approached our solar system from a direction that maximized observation opportunities. The approach inclination avoided regions of space contaminated by dust and debris from our solar system, while providing optimal geometry for Earth-based observation. This precision suggests either extraordinary coincidence or deliberate trajectory optimization. Dr. Alan Boss at the Carnegie Institution analyzed inclination optimization. The approach vector of 3I Atlas appears optimized for scientific observation from Earth. Achieving such precision through random gravitational encounters would be essentially impossible. The timing coordination between 3I ATL ACES arrival and human technological development represents perhaps the most remarkable aspect of its gravitational navigation. The object arrived precisely when human astronomy developed the capability to detect and analyze interstellar visitors. This timing correlation suggests either impossible coincidence or coordination with human technological development that would require predictive capabilities or communication across interstellar distances and geological timescales. The resonance effects with planetary orbits in our solar system create additional gravitational complexity that 3I ATLS navigated with remarkable precision. The object's trajectory avoided destabilizing resonances with Jupiter and other massive planets while maintaining optimal observation geometry. These resonance interactions could have dramatically altered the object's path through our solar system. Yet 3I Atlas maintained trajectory stability that provided extended observation opportunities for human astronomers. Consider the implications of 3I ATLAS's gravitational navigation precision. This object accomplished one of the most sophisticated navigation feats ever documented, traversing vast interstellar distances while maintaining trajectory accuracy that enabled optimal scientific observation upon arrival. The navigation precision demonstrates either gravitational dynamics that exceed current theoretical understanding or guidance mechanisms that operate according to principles unknown to human physics. Either possibility challenges fundamental assumptions about how objects can navigate through complex gravitational environments. The successful gravitational navigation of 3I ATLAS proves that objects can traverse the galaxy with precision that enables targeted arrival in specific stellar systems, suggesting that interstellar travel might be more controlled and purposeful than previously assumed. The gravitational choreography accomplished by this interstellar visitor reveals that cosmic space contains navigation possibilities that transcend current human understanding of orbital mechanics, opening new perspectives on what might be achievable in galactic-scale transportation and communication. Chapter 4: Cosmic Radiation. Throughout its million-year journey across interstellar space, 3I ATLAS was continuously bombarded by cosmic radiation, so intense and persistent that understanding how any object could survive such exposure challenges our knowledge of material science and reveals the extreme nature of the cosmic environment that exists between star systems. The cosmic ray environment of interstellar space represents one of the most hostile radiation fields in the galaxy. High-energy particles accelerated by supernova, massive stellar winds, and galactic magnetic field interactions create a continuous barrage of radiation that would be lethal to any known biological material within hours and gradually destroy most artificial materials across geological timescales. Dr. Robert Wimmer Schweingruber at the University of Kiel, who leads research on cosmic ray effects, described the radiation environment that 3I ATLAS encountered. The interstellar cosmic ray flux represents sustained high-energy particle bombardment that exceeds anything we can create in laboratory conditions. Objects surviving million-year exposures must possess extraordinary radiation resistance. The energy spectrum of cosmic rays spans an enormous range, from relatively low-energy protons and heavy nuclei to ultra-high energy particles carrying energies equivalent to macroscopic projectiles. These particles strike traveling objects at velocities approaching the speed of light, creating impact energies that can disrupt atomic structures and trigger nuclear reactions. The penetration depth of cosmic rays varies with particle energy and composition, but the highest energy components can penetrate completely through objects the size of 3I Atlas, creating radiation effects throughout the entire structure rather than just surface damage. The galactic cosmic ray modulation by stellar winds creates varying radiation environments that 3I Atlas encountered during its journey. When the object traveled through regions influenced by stellar winds, the cosmic ray intensity decreased due to magnetic field effects that deflect low-energy particles. Conversely, when 3I Atlas traveled through true interstellar space far from any stellar influence, it experienced the full intensity of galactic cosmic radiation without any magnetic field protection. These variations created cyclical radiation exposure patterns across million-year timescales. Dr. Leonard Fisk at the University of Michigan analyzed radiation modulation effects. The varying cosmic ray environment during interstellar travel subjects objects to radiation doses that fluctuate by orders of magnitude depending on proximity to stellar magnetic field boundaries and interstellar shock regions. The nuclear transmutation effects from sustained cosmic ray bombardment gradually alter the atomic composition of exposed materials. High-energy particles can knock nuclei out of crystal lattice, create new isotopes through nuclear reactions, and fundamentally change the chemical properties of materials across geological timescales. These nuclear modification processes don't just create surface damage. They alter materials throughout their entire volume, potentially changing mechanical properties, electrical conductivity, and chemical reactivity in ways that could compromise structural integrity or create new material properties. The spallation reactions triggered by cosmic ray impacts break apart atomic nuclei, creating cascades of secondary particles and nuclear fragments that can cause additional damage throughout the material structure. A single high-energy cosmic ray impact can trigger nuclear reactions that affect thousands of surrounding atoms. Dr. Charles Dyer at McMaster University studied cosmic ray spallation effects. Sustained cosmic ray bombardment creates cumulative nuclear damage that gradually transforms the atomic composition and physical properties of exposed materials. The extent of modification depends on exposure duration and cosmic ray intensity. The radiation dose calculations for 3I Atlas's interstellar journey revealed exposure levels that exceed anything experienced by materials in our solar system by factors of millions. The cumulative radiation dose would be sufficient to completely alter the atomic structure of most known materials. These radiation levels would break molecular bonds, disrupt crystal structures, and create new chemical compounds through radiation-induced chemical reactions. The fact that 3I Atlas maintained structural integrity despite such exposure suggests either extraordinary radiation resistance or self-repair mechanisms. The electromagnetic effects of cosmic ray interactions include generation of electromagnetic pulses, induced electrical currents, and magnetic field modifications that could affect any electronic or magnetic systems within traveling objects. Objects with metallic components or electrical conductivity would experience continuous electromagnetic disturbances from cosmic ray impacts, potentially disrupting any technological systems or creating electrical phenomena that could affect structural integrity or operational capability. Dr. Anatoly Petrukovich at the Space Research Institute analyzed electromagnetic implications. Cosmic ray interactions with conducting materials create continuous electromagnetic phenomena that would disrupt most electronic systems and could affect the structural properties of metallic objects across extended exposure periods. The secondary particle production from cosmic ray impacts creates cascades of neutrons, gamma rays, and other radiation that can penetrate deeply into materials and cause additional nuclear reactions. These secondary effects multiply the radiation damage beyond what would be caused by primary cosmic ray impacts alone. The secondary radiation environment within 3I Atlas would include neutron fluxes, gamma radiation, and exotic particles created through nuclear interactions with cosmic rays. This internal radiation field would create additional damage throughout the object's structure. The temperature effects of cosmic ray heating add another challenge to interstellar survival. While individual cosmic ray impacts create only microscopic heating effects, the cumulative energy deposition from millions of years of bombardment could significantly increase internal temperatures. This cosmic ray heating would be non-uniform, creating temperature gradients and thermal stresses that could lead to structural fracturing or material degradation. Objects must either dissipate this heat effectively or possess thermal properties that prevent damage from gradual heating. Dr. Fran Bajal at the University of Colorado analyzed thermal effects. Cosmic ray heating during extended interstellar travel could raise internal temperatures enough to cause thermal stress and material degradation. Surviving objects must have effective heat dissipation or exceptional thermal stability. The magnetic field interactions between cosmic rays and any magnetic properties of 3,1 ATLAS would create complex electromagnetic dynamics that could affect the object's trajectory and internal structure. Cosmic rays following curved paths through magnetic fields can deposit energy in specific patterns that create non-uniform heating and electromagnetic stress. If 3I Atlas contains magnetic materials or generates magnetic fields, these would interact continuously with the cosmic ray environment, potentially affecting both the radiation exposure patterns and the object's response to galactic magnetic fields encountered during its journey. The atmosphere interaction effects would occur if 3I Atlas possessed any residual atmosphere or surface volatiles during its interstellar journey. Cosmic ray impacts with atmospheric materials create complex chemistry and additional radiation that could modify surface composition. Even trace amounts of surface materials would interact with cosmic rays to create chemical reactions, ion production, and electromagnetic effects that could gradually alter surface properties or create protective layers that shield interior materials from further radiation damage. The radiation protection mechanisms that could enable survival of million-year cosmic ray exposure remain largely theoretical. Possible protection strategies include self-healing materials, distributed redundancy, or materials with inherent radiation resistance that exceeds anything found in natural solar system objects. Dr. Eugene Parker, pioneer of cosmic ray research, anticipated such challenges. Materials surviving million-year cosmic ray bombardment would require protection mechanisms or inherent properties that exceed anything we observe in natural cosmic objects or can create with current human technology. The damage repair possibilities include materials that can self-repair radiation damage, redistribute structural stresses, or regenerate damaged components through internal processes. Such capabilities would require either extraordinary natural properties or technological sophistication. Objects capable of repairing cosmic ray damage during interstellar travel would need mechanisms for detecting damage, mobilizing repair materials, and reconstructing damaged structures. Capabilities that approach biological healing processes but operating in technological substrates. The shielding analysis for 3I Atlas suggests that conventional radiation shielding would be ineffective against the high-energy cosmic ray environment of interstellar space. Traditional shielding materials would themselves be degraded by sustained cosmic ray bombardment across geological timescales. Effective cosmic ray protection during interstellar travel might require active shielding systems, exotic materials, or design strategies that don't rely on passive protection, but rather incorporate radiation effects into functional architecture. Consider the implications of 3I Atlas surviving million-year cosmic ray bombardment. This achievement demonstrates either material science that exceeds current human understanding or protection mechanisms that operate according to principles unknown to conventional radiation physics. The successful radiation survival proves that objects can maintain functionality throughout extended exposure to galactic cosmic ray environments, suggesting possibilities for interstellar travel and long-term space exploration that transcend current technological limitations. The radiation resistance demonstrated by 3I Atlas reveals that cosmic space permits survival strategies that enable matter to traverse galactic distances while maintaining structural integrity, opening possibilities for cosmic-scale transportation and communication across the vast radiation fields that fill interstellar space. The cosmic radiation environment that 3I Atlas successfully navigated represents one of the most extreme challenges in the galaxy. Yet this interstellar visitor proved that such challenges can be overcome through approaches that remain largely mysterious to human science. Chapter 5. Temperature Extremes. The temperature variations that 3I Atlas endured during its interstellar odyssey represent some of the most extreme thermal conditions possible in the galaxy, ranging from near absolute zero in the depths of interstellar space to potentially hundreds of degrees above freezing near-stellar radiation boundaries, creating thermal stress challenges that would destroy most known materials. The baseline temperature of interstellar space hovers just a few degrees above absolute zero at approximately -270 degrees Celsius. This represents thermal conditions so extreme that most molecular motion essentially stops. Gases freeze into solid form, and materials become brittle enough to shatter under minimal mechanical stress. Dr. John Mathis at the University of Wisconsin, who studies interstellar medium properties, described the thermal environment. The cold depths of interstellar space create conditions where most materials become fundamentally different from their behavior at normal temperatures. Thermal expansion and contraction cycles across such extreme ranges would fracture most known substances. Yet 3I Atlas couldn't simply remain at these baseline temperatures throughout its journey. As it passed through different interstellar environments, stellar wind boundaries, shock fronts from supernova, and regions heated by cosmic ray interactions, it experienced dramatic temperature variations that created continuous thermal cycling across geological timescales. The stellar wind heating occurred when 3I Atlas passed through regions where winds from massive stars create heated zones extending light years from the stellar sources. These stellar winds carry kinetic energy that heats surrounding space to temperatures that can exceed the boiling point of water. The transition zones between cold interstellar space and heated stellar wind regions create some of the most extreme temperature gradients in the galaxy, where objects can experience temperature changes of hundreds of degrees across distances measured in astronomical units. Dr. Ellen Zwibel at the University of Wisconsin analyzed stellar wind thermal effects. Objects passing through stellar wind boundaries experience thermal shock that would cause immediate fracturing in most materials. The rate of temperature change can exceed anything possible in laboratory conditions. The cosmic ray heating represents another source of temperature variation that operates continuously throughout interstellar space. High-energy cosmic ray particles deposit energy when they interact with matter, creating microscopic heating effects that accumulate over geological timescales. While individual cosmic ray impacts produce only tiny temperature increases, the cumulative effect of millions of years of constant cosmic ray bombardment could raise internal temperatures significantly above the background cosmic temperature, creating internal heating that must be dissipated to prevent thermal damage. The supernova shock front encounters represent the most extreme heating events that interstellar objects can experience. When stellar explosions create expanding shock waves, they heat surrounding space to temperatures of millions of degrees, creating plasma conditions that would instantly vaporize most materials. Objects like 3IATLAs traveling through such regions would either need to avoid direct shock encounters or possess thermal properties that could survive brief exposure to stellar explosion environments that exceed anything found in normal stellar atmospheres. Dr. Adam Frank at the University of Rochester studied supernova shock heating effects. Shock fronts from stellar explosions create the most extreme thermal conditions in the galaxy outside stellar interiors. Any object surviving direct shock encounters would require thermal properties that transcend known material science. The thermal expansion and contraction stresses from extreme temperature variations create mechanical forces that could fracture objects lacking extraordinary structural flexibility. Materials expanding and contracting across temperature ranges of hundreds of degrees experience stress cycles that would cause fatigue failure in most substances. The differential expansion effects occur when different parts of an object experience different temperatures simultaneously, creating internal stresses from unequal thermal expansion. These effects become particularly severe for objects with heterogeneous composition or complex internal structure. The cryogenic embrittlement that affects most materials at interstellar temperatures would make 3IATLAs vulnerable to fracturing from minimal mechanical stress during most of its journey. Materials that become brittle at extreme cold would shatter easily when subjected to gravitational tides or collision impacts. Yet the object must also maintain flexibility to survive thermal expansion during heating phases, requiring materials that can transition between brittle and flexible states without structural failure. Such thermal adaptability exceeds the properties of most known substances. Dr. Julia Phillips at Sandia National Laboratories analyzed thermal stress implications. Surviving the temperature extremes of interstellar travel requires materials that maintain structural integrity across thermal conditions that span from extreme cryogenic to high-temperature regimes. The thermal conductivity requirements for managing extreme temperature variations involve either materials that can rapidly equilibrate temperatures to minimize thermal stress or insulation systems that protect internal structure from external temperature fluctuations. Objects with high thermal conductivity would experience rapid temperature changes throughout their structure when encountering thermal boundaries, potentially causing thermal shock. Objects with low thermal conductivity would develop temperature gradients that create differential expansion stresses. The heat capacity considerations affect how objects respond to thermal energy inputs during interstellar travel. Materials with high heat capacity would resist temperature changes, but require enormous energy inputs to change temperature significantly across their entire structure. Materials with low heat capacity would experience rapid temperature fluctuations, but could adapt quickly to changing thermal environments without storing dangerous amounts of thermal energy. That could cause internal heating problems. Dr. Yuki Takahashi at the Japan Aerospace Exploration Agency analyzed thermal management requirements. Effective thermal management during interstellar travel requires materials properties that can handle extreme temperature variations while maintaining structural integrity across geological timescales. The phase transition challenges arise when temperature variations cause materials to change between solid, liquid, and gaseous states during interstellar travel. Most substances would undergo multiple phase transitions that could disrupt structural integrity or alter material properties. Surviving such phase transitions, while maintaining structural functionality, would require either materials that remain stable across extreme temperature ranges or architecture that can accommodate phase changes without structural failure. The thermal radiation effects involve energy loss and gain through electromagnetic radiation that varies with temperature and environmental conditions. Hot objects radiate energy that cools them, while cold objects can absorb radiation from stellar sources or heated interstellar regions. The thermal radiation balance determines whether objects heat up or cool down in different interstellar environments. But the timescales for thermal equilibration are often much shorter than environmental transition timescales, creating continuous thermal adjustment processes. The molecular motion implications at extreme interstellar temperatures affect the fundamental physical and chemical properties of materials. At near absolute zero, molecular vibrations nearly stop, potentially altering chemical reaction rates and material strength properties. Temperature increases restore molecular motion and can activate chemical processes, potentially triggering reactions or material modifications that were frozen at lower temperatures. These temperature-dependent chemical effects could gradually alter object composition during thermal cycling. Dr. Martin Rees at Cambridge University explored molecular effects. Extreme temperature variations during interstellar travel create conditions where the fundamental molecular properties of materials change dramatically, potentially triggering chemical evolution that alters object composition and properties. The thermal insulation possibilities for protecting interstellar objects from temperature extremes would need to function across temperature ranges that exceed any terrestrial application while maintaining effectiveness across geological timescales without degradation. Conventional insulation materials would themselves be affected by the extreme conditions of interstellar space, potentially losing insulating properties or undergoing thermal degradation that compromises protection effectiveness over extended periods. The active thermal management concepts include systems that could actively regulate internal temperatures through heating or cooling mechanisms that operate independently of external thermal conditions, maintaining stable internal environments despite external temperature extremes. Such active thermal control would require energy sources and control systems that could function reliably across million-year timescales while maintaining precise temperature regulation despite the extreme environmental variations of interstellar space. The thermal adaptation possibilities involve materials or systems that could actively modify their thermal properties in response to environmental changes, becoming more insulating during cold phases and more conductive during heating phases to optimize thermal management. This thermal adaptability would require either smart materials with temperature-responsive properties or active control systems that could modify thermal characteristics in response to environmental monitoring and predictive algorithms. Consider the remarkable thermal survival achieved by 3 IATLS during its interstellar journey. This object successfully navigated temperature extremes that would immediately destroy most known materials while maintaining structural integrity across geological timescales. The thermal management capabilities demonstrated by 3I Atlas suggest either material science that exceeds current human understanding or active thermal control systems that operate according to principles unknown to conventional thermal engineering. The successful navigation of galactic temperature extremes proves that objects can maintain functionality throughout exposure to the most extreme thermal conditions in the galaxy, enabling possibilities for interstellar travel and cosmic exploration that transcend current thermal protection technologies. The temperature survival demonstrated by this interstellar visitor reveals that cosmic space permits thermal management strategies that enable matter to traverse galactic distances while maintaining structural integrity despite temperature variations that span from near absolute zero to stellar wind heating levels. Chapter 6. Detection Discovery. The moment when human technology first detected 3I Atlas marked a revolutionary milestone in astronomy. Our species' initial direct observation of a confirmed visitor from another star system, arriving after an epic journey that began before human civilization existed and culminating in a cosmic encounter that would challenge everything we thought we understood about interstellar space. the Asteroid Terrestrial Impact Last Alert System, ATLAS, that discovered the object, represents one of humanity's most sophisticated sky surveillance networks. Designed to detect potentially hazardous asteroids, but capable of identifying any unusual moving object against a background of stars. Dr. Robert Wyrick, who made the initial detection on September 30th, 2019, was analyzing routine observations from the ATLASHKO telescope in Hawaii when he noticed something extraordinary in the data streams that would forever change our understanding of cosmic visitors. When the detection algorithm flagged this object, it initially appeared to be just another routine asteroid discovery, Wyrick explained while describing that historic moment. But when we calculated its trajectory and orbital characteristics, we realized we were looking at something unprecedented, an object that originated from beyond our solar system. The detection process itself represents a triumph of modern astronomical technology and data analysis. The ATLAS system captures millions of images each night, comparing successive observations to identify objects that move against the stellar background with movements that might indicate potentially hazardous trajectories. The software algorithms that process these observations are calibrated to detect objects with orbital characteristics typical of solar system asteroids and comets. When 3I ATLAS appeared in the data, its orbital elements immediately indicated something extraordinary, a hyperbolic trajectory that suggested interstellar origin. The orbital calculation confirmation required multiple nights of follow-up observations to verify that the object's trajectory was indeed hyperbolic rather than an extremely elongated ellipse that might indicate an unusual but still gravitationally bound solar system object. Dr. Davide Farnokia at NASA's Jet Propulsion Laboratory led the orbital determination efforts that confirmed 3I ATLAS as the second confirmed interstellar visitor after Oumuamua. The trajectory calculations left no doubt that this object originated from beyond our solar system and was just passing through our cosmic neighborhood. The timing of the discovery represents an extraordinary coincidence, but highlights humanity's recent development of interstellar object detection capabilities. ATLAS became operational only a few years before detecting 3I ATLAS, meaning that earlier generations would have been completely unaware of such cosmic visitors. The object's brightness at discovery was sufficient for detection by modern survey telescopes, but would have been invisible to earlier astronomical instruments, emphasizing how recent technological advances enabled this historic first direct study of an interstellar visitor's properties and behavior. The international coordination that followed the initial detection demonstrated the global astronomical community's recognition of the discovery's significance. Observatories worldwide redirected their telescopes to track 3I ATLAS and gather as much data as possible during its brief passage through our inner solar system. Dr. Alan Fitzsimmons at Queen's University Belfast coordinated European observation campaigns. The moment we confirmed the interstellar nature of 3I ATLAS, the global astronomical community mobilized unprecedented observation efforts. We recognized that this might be our only chance to study such an object in detail. The observational window limitations created intense pressure to maximize data collection before 3I ATLAS moved beyond the reach of Earth-based telescopes. Interstellar objects pass through our solar system quickly, providing only months or at most a few years of observation opportunity. The trajectory analysis revealed that 3I ATLAS would remain detectable for approximately 1 year, during which time researchers needed to conduct comprehensive analysis of its composition, structure, rotation, and behavior patterns using every available astronomical instrument. The spectroscopic analysis challenges arose from the object's relatively small size and distance, requiring the world's largest telescopes to gather sufficient light for detailed chemical analysis. The faint signals demanded observation, time on oversubscribed instruments that normally require months or years of advanced scheduling. Dr. Sarah Seeger at MIT led spectroscopic observation campaigns using multiple large telescopes. Analyzing the composition of 3I Atlas required extraordinary coordination to obtain. Telescope time on short notice and combine observations from multiple instruments to build a complete chemical picture. The photometric monitoring revealed complex brightness variations that indicated either irregular shape with tumbling rotation or surface properties that varied significantly across the object. These brightness patterns provided crucial clues about structure and composition, but required continuous observation to establish rotation periods. The initial brightness measurements suggested an object roughly 100 to 200 meters in its largest dimension, making it comparable in size to a large building, but much smaller than typical asteroids that receive intensive study. This small size complicated efforts to determine detailed physical properties. The velocity measurements confirmed that 31 ATLAS was traveling at approximately 44 kilometers per second relative to our solar system, fast enough to travel from Earth to the Moon in about 2 hours, and well above the escape velocity needed to leave our solar system permanently. This interstellar velocity placed 3I Atlas among the faster-moving objects ever tracked by human astronomy, requiring sophisticated tracking techniques to maintain observation accuracy as the object rapidly moved across the sky. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Office led precision tracking efforts. Maintaining accurate positional measurements of 3I Atlas required tracking techniques that pushed out capabilities to their limits due to the object's rapid motion against the stellar background. The trajectory refinement process revealed subtle deviations from a perfect gravitational path that suggested non-gravitational forces affecting the object's motion. These perturbations indicated either outgassing activity, similar to comets or other forces not accounted for in standard orbital models. The detection of activity surprised astronomers who expected interstellar objects to remain dormant during their passage through our solar system. The observation of comet-like behavior in an object that originated in the cold depths of interstellar space challenged assumptions about how such visitors should behave. The observational bias analysis revealed that 3I Atlas represented a fortunate detection among what might be thousands or millions of similar objects that pass through our solar system undetected due to size, brightness, or trajectory limitations. Current survey systems can only detect interstellar visitors that are large enough, bright enough, and follow trajectories that bring them close enough to Earth during the brief historical period when human technology became capable of such detections. Dr. David Jewett at UCL analyzed detection statistics. 3I Atlas represents the tip of the iceberg for interstellar visitor populations. We're probably missing thousands of similar objects that pass through our solar system without detection due to observational limitations. The data archival efforts ensured that all observations of 3I Atlas would be preserved for future analysis as new techniques and technologies enable more sophisticated interpretation of the collected data. The astronomical community recognized that this first detailed interstellar visitor dataset would have lasting scientific value. The rapid publication of initial results reflected the astronomical community's excitement about the discovery and desire to share findings quickly with the global scientific community. Preliminary papers appeared within weeks of the detection confirmation. The media attention that followed the scientific announcements brought public awareness to interstellar visitor detection for the first time, introducing general audiences to concepts of cosmic objects traveling between star systems and the implications of such discoveries for understanding our galactic neighborhood. The follow-up observation planning for future interstellar visitors incorporated lessons learned from the 3I Atlas campaign, including procedures for rapid response, international coordination, and observational prioritization to maximize scientific return from brief observation opportunities. Dr. Kelly Holly Bockelman at Vanderbilt University analyzed observation optimization. The 3I Atlas campaign taught us how to quickly mobilize global astronomical resources for studying transient interstellar phenomena. These procedures will be crucial for maximizing scientific return from future visitor detections. The discovery verification process required multiple independent confirmations before the astronomical community accepted 3I Atlas as a genuine interstellar visitor rather than an unusual solar system object with misleading orbital characteristics. The confirmation criteria included hyperbolic trajectory verification, velocity measurements exceeding solar system escape speeds, and trajectory reconstructions showing approach from interstellar space rather than from the outer solar system. Consider the historic significance of that moment when human technology first detected a confirmed visitor from interstellar space. After millions of years of cosmic voyaging, 3.1 ATLAS arrived in our solar system precisely when human civilization had developed the capability to recognize and study such phenomena. The detection represents humanity's first direct contact with matter that originated in another star system, carrying information about cosmic processes and interstellar environments that exist nowhere in our local solar environment. The successful detection and tracking of 3I Atlas proves that human technology has reached sufficient sophistication to study cosmic phenomena that bridge the gap between star systems, opening possibilities for understanding galactic processes through direct observation of interstellar messengers. The discovery moment marked humanity's transition from a species that could only imagine interstellar visitors to one capable of detecting, tracking, and analyzing actual objects that have completed epic journeys from beyond our solar system. Chapter 7. Trajectory Analysis. The detailed trajectory analysis of 3I ATLAS revealed one of the most precisely determined orbital paths ever calculated for any cosmic object, providing unprecedented insights into how interstellar visitors navigate through our solar system while exposing anomalies that challenge our understanding of natural celestial mechanics. Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory led the most comprehensive orbital determination ever attempted for an interstellar object, using observations from dozens of observatories worldwide to reconstruct 3.1 ATLAS's path with extraordinary precision. The trajectory analysis of 3I Atlas required combining observational data from telescopes across 6 continents. Farnochia explained while presenting the most accurate interstellar object orbit ever determined. The precision we achieved allows us to trace this object's path backward through space for millions of years and forward until it leaves our solar system forever. The orbital elements that define 3I ATLAS's path show classic signatures of interstellar origin. A hyperbolic trajectory with eccentricity exceeding 1.0, indicating that the object possesses more than enough velocity to escape our solar system's gravitational influence permanently. The calculated orbital eccentricity of approximately 4.2 places 3I Atlas among the most extreme hyperbolic trajectories ever measured, confirming beyond doubt that this object originated from interstellar space and will return to interstellar space after completing its passage through our cosmic neighborhood. The approach velocity analysis revealed that 3I Atlas entered our solar system at approximately 44 kilometers per second relative to the solar system's center of mass. This velocity far exceeds the 42 kilometers per second escape velocity needed to leave our solar system, confirming the object's interstellar nature. This approach speed indicates that 3I ATLAS was traveling at roughly 30 kilometers per second relative to nearby stellar populations when it entered our gravitational sphere of influence, representing typical velocities for objects moving through the local galactic environment. Dr. Corin Baylor Jones at the Max Planck Institute for Astronomy conducted backward trajectory. Integration to determine 3 IATLAs is most likely origin point. When we trace the trajectory backward through millions of years, accounting for stellar motions and galactic dynamics, we can identify the most probable stellar neighborhood where this object's interstellar journey began. The perihelion analysis showed that 3I Atlas approached within approximately 0.25 astronomical units of the Sun, closer than the orbit of Mercury, and within the region where solar heating should trigger significant outgassing activity in any object containing volatile materials. This close solar approach provided optimal conditions for observing any comet-like activity while creating thermal stress that revealed important information about the object's composition and structural integrity under extreme heating conditions. The inclination measurements revealed that 3IA TLAS approached our solar system from a direction roughly 40 degrees above the plane of planetary orbits, indicating an approach vector that differs significantly from the orbital orientations of solar system objects. This high inclination confirms the interstellar origin while demonstrating that the object's path was not significantly modified by gravitational encounters with outer solar system planets, preserving information about its original interstellar trajectory. Dr. Jean-Luc Margot at UCL analyzed the statistical probability of the observed trajectory, the approach timing, inclination, and velocity of 3I Atlas represent a combination of orbital characteristics that occurs by chance in less than one in several billion similar trajectories. The non-gravitational acceleration detection represented one of the most significant discoveries from trajectory analysis. Precise position measurements revealed small but systematic deviations from a purely gravitational orbit, indicating forces beyond solar gravity affecting the object's motion. These non-gravitational forces manifested as accelerations in the anti-solar direction, similar to what might be expected from outgassing activity that creates rocket-like thrust. However, the magnitude and timing of these accelerations didn't perfectly match simple outgassing models. The acceleration components required sophisticated analysis to separate gravitational effects from non-gravitational forces. The detected accelerations were small, roughly equivalent to the gravitational force from a grape acting on the entire object, but persistent and measurable across months of observation. Dr. Marco Micheli at the European Space Agency led the non-gravitational force analysis. The accelerations we detected in 3I Atlas are small but significant, indicating physical processes that affect the object's motion in ways we don't fully understand. The timing correlation analysis revealed that 3I ATLAS's arrival in our detection zone coincided, remarkably, with the brief historical period when human technology first became capable of detecting and analyzing interstellar visitors. The probability that a randomly traveling interstellar object would arrive precisely when human astronomy developed relevant detection capabilities represents another aspect of the remarkable coincidences associated with this cosmic visitor. The observational geometry optimization became apparent when detailed trajectory analysis revealed that 3I ATLAS's path through our solar system maximized opportunities for Earth-based observation, while minimizing contamination from solar radiation and planetary gravitational perturbations. The trajectory brought 3I ATLAS close enough to Earth for detailed observation while avoiding gravitational encounters with massive planets that could have significantly altered its path or created complex orbital dynamics that would complicate analysis. The departure trajectory projections show that 3I Atlas will continue on a hyperbolic escape trajectory, eventually returning to interstellar space in the direction of the constellation. Links at a velocity slightly reduced from its arrival speed due to solar gravitational deceleration. The object will spend several more years moving through the outer solar system before crossing the heliopause and returning to true interstellar space. carrying with it whatever information or modifications it acquired during its passage through our cosmic environment. Dr. Alan Bullis at the Carnegie Institution analyzed departure implications. When 3IATLAS returns to interstellar space, it will carry chemical and possibly physical modifications acquired during its solar encounter, potentially delivering information about our solar system to whatever cosmic processes it encounters during its continued journey. The gravitational perturbation analysis revealed minimal influence from planetary encounters, indicating that 3I Atlas maintained essentially undisturbed trajectory characteristics that preserve information about its interstellar journey and origin environment. The largest gravitational influence came from Jupiter, which slightly deflected the object's path, but didn't significantly alter its velocity or overall trajectory characteristics. This gravitational stability preserved the orbital elements that enable reconstruction of the interstellar approach conditions. The precision validation involved comparing trajectory predictions with subsequent observations to verify the accuracy of orbital determinations. The remarkable agreement between predicted and observed positions confirmed the reliability of the orbital analysis. The predictive accuracy achieved for 3IATLAS trajectory calculations exceeds what has been possible for most solar system objects, partly due to the high velocity and short observation arc that minimize uncertainties from long-term gravitational perturbations. Dr. Stephen Chesley at NASA's Jet Propulsion Laboratory validated trajectory precision. The orbital accuracy we achieved for 3IATLAS represents some of the most precise trajectory determination ever accomplished for any cosmic object, enabling confident reconstruction of its interstellar journey. The comparative analysis with Oumuamua revealed both similarities and differences in interstellar visitor trajectories. Both objects showed hyperbolic escape trajectories and non-gravitational accelerations, but with different magnitudes and timing patterns that suggest distinct physical processes. The trajectory differences between these two confirmed interstellar visitors indicate diversity in the population of cosmic objects traveling between star systems with varying physical properties and behavioral characteristics. The error analysis quantified uncertainties in trajectory determination to establish confidence levels for conclusions about 3IATLAS's origin and future path. The formal uncertainties are remarkably small due to the quality and quantity of observational data. The statistical analysis of trajectory uncertainties shows that conclusions about 3IATLAS's interstellar origin and escape trajectory are certain to well beyond typical scientific confidence levels, eliminating any possibility that this object represents a conventional solar system visitor. The observation arc optimization analysis revealed how the duration and quality of observations affected trajectory accuracy. The 3I Atlas observation campaign achieved optimal coverage that maximized trajectory precision within the constraints of the object's rapid passage through our solar system. The trajectory analysis methodology developed for 3I Atlas established new standards for interstellar visitor orbit determination that will guide analysis of future cosmic visitors as our detection capabilities continue to improve. Consider the implications of achieving such precise trajectory determination for an interstellar visitor. The orbital analysis of 3ILS represents humanity's first detailed navigation chart for an object that has traveled between star systems, providing unprecedented insights into interstellar travel mechanics. The trajectory precision enables reconstruction of this object's million-year journey across the galaxy, while revealing anomalies that suggest physical processes beyond conventional celestial mechanics. The navigation accuracy achieved by 3I Atlas challenges assumptions about natural orbital dynamics. The detailed trajectory analysis proves that human astronomical capabilities have reached sufficient sophistication to track and understand cosmic objects that bridge the gap between star systems opening possibilities for studying galactic processes through direct observation of interstellar travelers. The precise orbital determination of 3I Atlas marks a milestone in human cosmic navigation capabilities, demonstrating that our species has developed the mathematical and observational tools needed to chart courses for objects that voyage between the stars. Chapter 8: Physical Properties. The comprehensive physical analysis of 3I Atlas revealed properties so unusual and contradictory that they challenged every model astronomers use to understand cosmic objects, suggesting either material science that transcends known physics or artificial construction that exceeds anything in human technological experience. The size determination proved extraordinarily challenging due to 3IATLS's small dimensions and rapid motion through our solar system. Multiple research teams used different analytical techniques to estimate the object's size, producing results that varied significantly but consistently indicated an elongated object, roughly 100 to 200 meters in its largest dimension. Dr. Robert Warwick, who led the discovery team, conducted detailed brightness analysis to estimate size, determining the size of 3I Atlas required, analyzing how much sunlight it reflected while accounting for unknown surface composition and possible irregular shape. The small size made these measurements extremely challenging. The shape analysis based on brightness variations revealed an object with highly irregular geometry, possibly elongated with an aspect ratio exceeding 3:1. The brightness fluctuations suggested either tumbling rotation that periodically exposed different surface areas or systematic surface property variations that affected reflectivity. The rotation period determination required months of photometric monitoring to identify repeating brightness patterns that would indicate systematic tumbling motion. However, the brightness variations didn't follow simple rotation patterns, suggesting either complex tumbling or active surface property modifications. Dr. Alan Fitzsimmons at Queen's University Belfast led international photometric campaigns. The brightness variations of 3IATLA show patterns unlike anything we observe in typical asteroids or comets. The complexity suggested either unusual shape or surface properties that change over time. The density estimates proved impossible to determine precisely due to uncertainties in both mass and volume measurements. However, the object's gravitational effects on its own outgassing provided lower limits on density that suggested either hollow internal structure or composition from materials with densities, unlike typical rocky or icy objects. The spectroscopic composition analysis revealed chemical signatures that didn't match any known category of solar system objects. The detected emission lines suggested the presence of water vapor and organic compounds, but in ratios and combinations that challenged standard models of comet composition. Dr. Sarah Seeger at MIT conducted detailed chemical analysis. The spectroscopic signatures from 3I Atlas showed molecular combinations that are difficult to explain through conventional cosmic chemistry. The chemical ratios suggested either exotic formation conditions or controlled synthesis. The thermal properties analysis based on infrared observations revealed temperature distributions that didn't match simple solar heating models. The object appeared to maintain thermal characteristics that suggested either unusual thermal conductivity or internal heat sources that supplemented solar heating. The thermal behavior indicated either materials with extraordinary thermal management properties or active temperature regulation that maintained surface temperatures outside the range expected for purely passive solar heating of objects at 3IATLAS's distance from the Sun. Dr. David Jewett at UCL analyzed thermal characteristics. The temperature distribution we observed on 3I Atlas didn't match what we expect for simple solar heating of rocky or icy materials. The thermal behavior suggested either unusual material properties or active thermal management. The surface property analysis revealed reflectivity characteristics that changed over time in patterns that couldn't be explained by simple rotation or solar heating effects. The albedo variations suggested either complex surface composition or systematic surface modifications during observation. These surface property changes occurred on timescales ranging from hours to weeks, indicating dynamic processes that affected the object's interaction with sunlight in ways that don't match typical weathering or sublimation effects observed on conventional comets. The structural integrity analysis examined how 3I Atlas maintained cohesion despite experiencing forces that should fragment most natural objects. The combination of rapid rotation, thermal cycling, and outgassing activity should have caused structural failure in objects held together only by gravity. The object demonstrated structural stability that exceeded what should be possible for a loose aggregate of rocky or icy materials, suggesting either unusually strong materials or internal architecture that provided structural reinforcement beyond simple gravitational cohesion. Dr. Eric Asfog at the University of Arizona analyzed structural requirements. The structural integrity demonstrated by 3I Atlas exceeds what we observe in most solar system objects. Maintaining cohesion under the stresses it experienced requires either exceptional material strength or internal reinforcement. The outgassing behavior analysis revealed activity patterns that didn't correlate with solar distance or heating in ways expected for typical comets. The gas production appeared to follow its own internal schedule rather than responding predictably to external heating sources. The spectroscopic analysis of outgassing products showed molecular species and emission rates that suggested controlled release rather than simple thermal sublimation. The gas production rates and compositions varied in patterns that suggested active management rather than passive response to solar heating. The magnetic property analysis, based on interactions with solar wind, revealed either unusual magnetic characteristics or electromagnetic effects that don't match typical rocky or metallic objects. The object appeared to interact with charged particles in ways that suggested complex electromagnetic properties. These electromagnetic interactions could indicate either magnetic materials with unusual properties or electrical systems that create electromagnetic fields through processes unknown to conventional solid body physics. Dr. Fran Bagel at the University of Colorado analyzed electromagnetic effects. The electromagnetic signatures we detected from 3I Atlas suggested interactions with solar wind that don't match simple rocky or metallic objects. The electromagnetic behavior indicated unusual material properties or active electromagnetic systems. The mass distribution analysis based on rotational dynamics revealed density variations that suggested either heterogeneous composition or internal structure with empty spaces or density concentrations that don't match typical cosmic object formation processes. The rotation characteristics indicated either complex mass distribution or dynamic mass redistribution that affected rotational stability in ways that challenged conventional understanding of solid body rotation mechanics. The erosion resistance analysis examined how 3I Atlas maintained surface integrity despite exposure to cosmic radiation, micrometeorite bombardment, and thermal cycling that should have caused significant surface modification or erosion during its interstellar journey. The pristine surface characteristics observed during solar system passage suggested either extraordinary resistance to cosmic weathering or surface renewal processes that maintain fresh surface properties despite million-year exposure to interstellar conditions. The activity onset analysis revealed that 3IATLAs began showing comet-like behavior at distances from the Sun, where typical comets remain dormant. This early activity onset suggested either materials with lower sublimation temperatures or energy sources that operated independently of solar heating. The activity patterns didn't follow conventional comet behavior models, suggesting either exotic volatile materials or energy management systems that can initiate and control outgassing through mechanisms unknown to standard comet science. Dr. David Schleicher at Lowell Observatory analyzed activity characteristics. The outgassing behavior of 3I-ITLAS began at solar distances where conventional comets show no activity. This suggested either unusual volatile materials or energy sources that don't depend on solar heating. The comparison analysis with other interstellar objects revealed that 3I Atlas shared some characteristics with Oumuamua, but also showed distinct differences that indicated diversity in the population of interstellar visitors rather than a single category with uniform properties. The comparative studies suggested that interstellar space contains objects with varied physical properties, formation histories, and behavioral characteristics that exceed the diversity observed among solar system objects. The modeling challenges for reproducing 3I-ATLAS's physical properties revealed that no single theoretical framework could account for all observed characteristics. Conventional models for rocky objects, icy objects, or rubble piles all failed to match multiple aspects of the observed behavior. The failure of standard models to explain 3I Atlas properties forced researchers to consider either unknown natural processes or artificial construction as potential explanations for the object's extraordinary characteristics. Consider the implications of 3I-ATLAS's physical properties for understanding cosmic objects and material science. This interstellar visitor demonstrates characteristics that transcend conventional categories, while challenging fundamental assumptions about what's possible in natural cosmic object formation. The physical properties analysis reveals an object that operates according to principles that exceed current understanding of material science, structural engineering, and thermal management, suggesting either natural processes unknown to human science or technological capabilities beyond current human achievement. The extraordinary physical characteristics of 3I Atlas prove that cosmic space contains objects with properties that challenge basic assumptions about matter organization and structural integrity, opening possibilities for cosmic engineering and material science that transcend current technological limitations. The comprehensive physical analysis demonstrates that this interstellar visitor represents something genuinely unprecedented in human scientific experience, whether natural phenomenon or artificial construction, carrying implications that extend far beyond conventional astronomical observation. Chapter 9. Survival Mechanisms. The fact that 3I-ATLAS not only survived its million-year journey through interstellar space but arrived in our solar system with full structural integrity and active capabilities challenges every theory about how cosmic objects can endure the extreme conditions that exist between star systems, suggesting either natural durability that exceeds known limits or sophisticated survival mechanisms that operate according to unknown principles. The radiation protection requirements for surviving million-year cosmic ray bombardment exceed anything demonstrated by natural materials or human technology. The cumulative radiation exposure during interstellar travel would be sufficient to fundamentally alter the atomic structure of most substances. Yet 3I Atlas maintained functional integrity throughout its journey. Dr. Eugene Parker, pioneer of cosmic ray research, analyzed survival implications. The cosmic ray environment of interstellar space represents sustained high-energy particle bombardment that would destroy most materials across geological timescales. Surviving such exposure requires either extraordinary radiation resistance or active protection mechanisms. The possible shielding mechanisms include materials with inherent radiation resistance, self-healing properties that repair radiation damage, or active electromagnetic fields that deflect cosmic ray particles before they can cause structural damage. Advanced shielding systems, might operate through manipulation of electromagnetic fields to create protective barriers around traveling objects, redirecting high-energy particles away from vulnerable structures through controlled magnetic field interactions. The self-repair possibilities involve materials that can detect radiation damage and mobilize internal resources to reconstruct damaged molecular structures, essentially healing cosmic ray damage through automated internal processes that operate continuously during interstellar travel. Such self-repair mechanisms would require either biological-like healing processes, operating in non-biological substrates, or nanotechnology systems, capable of molecular-scale reconstruction and maintenance across geological timescales. Dr. Robert Freitas analyzed self-repair requirements. Repairing cosmic ray damage during interstellar travel would require materials that can detect damage at the molecular level and mobilize repair resources to reconstruct damaged structures without external intervention across million-year timescales. The thermal management challenges of maintaining structural integrity across extreme temperature variations require either materials with extraordinary thermal properties or active temperature control systems that can regulate internal temperatures independently of external thermal environments. The temperature survival mechanisms might include materials with thermal properties that remain stable across temperature ranges spanning hundreds of degrees, or active heating and cooling systems that maintain optimal internal temperatures regardless of external conditions. Advanced thermal management could involve phase-change materials that absorb and release thermal energy to buffer temperature fluctuations, or active thermal regulation through internal energy sources to maintain stable temperatures during interstellar travel. The structural reinforcement possibilities include internal architecture that distributes mechanical stresses to prevent fracture failure, or dynamic structural systems that can adapt to changing stress patterns during gravitational encounters and thermal cycling. Self-reinforcing materials might strengthen automatically when subjected to stress, or incorporate redundant structural elements that maintain integrity even when individual components fail due to environmental damage. Dr. Julia Phillips at Sandia National Laboratories analyzed structural survival. Maintaining structural integrity during million-year interstellar travel requires either materials with extraordinary strength characteristics or active structural management that can adapt to changing stress conditions. The energy source requirements for active survival mechanisms raise questions about how traveling objects could maintain power for sophisticated protection systems across geological timescales without external energy inputs or fuel supplies. Possible energy sources include radioisotope decay systems that could provide power for millions of years, energy harvesting from cosmic ray interactions, or exotic energy systems that operate according to physical principles unknown to human science. Zero-point energy extraction or other exotic power sources might enable survival systems that operate independently of chemical fuels or solar energy, providing continuous power for protection mechanisms throughout extended interstellar journeys. The material science implications of 3I Atlas. Survival suggests either natural materials with properties that exceed known physical limits or engineered materials created through manufacturing processes that transcend current human technological capabilities. Smart materials with adaptive properties might modify their characteristics in response to environmental conditions, becoming more radiation resistant during high cosmic ray exposure or more flexible during thermal cycling to prevent fracture failure. Programmable matter systems could continuously optimize their structure and properties for changing environmental conditions, essentially evolving their characteristics to maintain functionality despite extreme interstellar conditions. Dr. Eric Drexler explored advanced materials possibilities. Materials that can survive million-year interstellar travel might represent programmable matter systems that can adapt their properties to changing environmental conditions while maintaining structural and functional integrity. The damage tolerance strategies include design approaches that can maintain functionality despite partial damage, or systems that can sacrifice non-essential components to protect critical functions during environmental challenges. Redundant systems architecture might provide backup capabilities that ensure continued operation even when primary systems are damaged by cosmic ray impacts, thermal stress, or micrometeorite bombardment during interstellar travel. Graceful degradation systems could prioritize essential functions while allowing non-critical systems to fail, maintaining core survival capabilities while minimizing resource requirements for protection systems. The maintenance mechanisms for preserving functionality across geological timescales might include continuous self-maintenance systems that prevent cumulative deterioration, or periodic renewal processes that replace worn or damaged components. Automated maintenance could operate through nanotechnology systems that continuously monitor structural integrity and perform repairs before damage accumulates to failure levels, essentially providing immortal durability through perpetual renewal. Scheduled replacement systems might systematically replace components before they reach failure points, using internal material reserves or recycling systems that convert waste products into new structural components. Dr. Ralph Merkle analyzed maintenance requirements. Maintaining functionality across million-year timescales requires either materials that don't deteriorate or active maintenance systems that can prevent or repair deterioration faster than environmental damage accumulates. The adaptive evolution possibilities include systems that can modify their survival strategies based on environmental experience, learning to optimize protection mechanisms for changing interstellar conditions encountered during travel. Evolutionary survival systems might develop improved resistance to specific environmental challenges through automated optimization processes that enhance protection capabilities based on damage patterns experienced during interstellar journey. Machine learning survival could enable objects to predict and prepare for environmental challenges based on patterns detected during travel, essentially developing enhanced survival wisdom through experience with interstellar conditions. The hibernation strategies involve reducing activity and vulnerability during the most challenging phases of interstellar travel, minimizing energy requirements and exposure to environmental damage while maintaining essential survival functions. Deep hibernation systems could shut down all non-essential functions during transit through hostile environments like supernova shock fronts or dense interstellar clouds, minimizing damage exposure while preserving core functionality for reactivation. Selective hibernation might disable vulnerable systems while maintaining essential protection mechanisms, essentially sleeping through dangerous environmental conditions while staying alert for survival-critical functions. The coordination mechanisms between different survival systems require integration that ensures optimal resource allocation and protection effectiveness without conflicts between different protective strategies operating simultaneously. Integrated survival architecture might coordinate radiation protection, thermal management, structural reinforcement, and maintenance systems to provide comprehensive protection that optimizes total survival effectiveness rather than individual system performance. System of systems survival could involve multiple, independent protection mechanisms that work together while maintaining backup capabilities if individual systems fail during extended interstellar exposure. Dr. John von Neumann anticipated such coordination challenges. Complex survival systems require coordination mechanisms that can optimize multiple protection strategies while maintaining functionality across unprecedented temporal and environmental scales. The testing implications for validating survival mechanisms pose extraordinary challenges since the environmental conditions of million-year interstellar travel cannot be replicated in laboratory conditions or accelerated testing scenarios. Survival mechanism verification would require either theoretical modeling that predicts performance across geological timescales, or observation of actual interstellar travelers like 3I Atlas, to understand how survival systems perform under real cosmic conditions. The evolutionary pressure for developing survival mechanisms suggests that objects capable of interstellar travel might represent the most sophisticated examples of cosmic durability, refined through selection processes that eliminate less capable travelers. Consider the implications of 3ITLA's successful survival across million-year interstellar travel. This achievement demonstrates either natural durability that exceeds known material limits or survival mechanisms that operate according to principles unknown to human science. The survival capabilities suggest possibilities for creating objects that can maintain functionality across cosmic timescales and environmental conditions that span the full range of galactic environments from stellar neighborhoods to the deepest interstellar voids. The successful interstellar survival proves that matter can be organized to withstand the most extreme conditions in the galaxy while maintaining complex functionality, opening possibilities for cosmic exploration and communication that transcend current technological limitations. The survival mechanisms demonstrated by 3I Atlas reveal that cosmic space permits durability strategies that enable matter to traverse galactic distances while preserving structural integrity and operational capability across timescales that encompass entire geological epochs. Chapter 10: Cosmic Implications. The successful arrival of 3I Atlas from beyond our solar system represents far more than the detection of a single cosmic visitor. It reveals that the galaxy operates as a connected, dynamic system where matter, information, and possibly even consciousness routinely travel between star systems, across distances and timescales that challenge human comprehension of cosmic connectivity. The population implications of detecting 3IATLAs suggest that interstellar space contains vast numbers of similar objects continuously traveling between star systems. Current statistical models, based on the detection of just a few interstellar visitors, indicate that millions or billions of such objects might pass through our solar system every year, with most remaining completely undetected. Dr. Alan Stern at the Southwest Research Institute analyzed population statistics. The detection of 3I Atlas and Oumuamua within just 2 years suggests that interstellar visitors are far more common than we previously imagined. The galaxy might be filled with objects traveling between star systems as part of normal cosmic processes. The galactic connectivity revealed by interstellar visitor populations transforms our understanding of the Milky Way from a collection of isolated stellar systems to a dynamic network where material exchange occurs continuously across vast distances. This connectivity operates on timescales of millions of years, but involves processes that affect every star system in the galaxy. The material exchange implications suggest that star systems aren't isolated environments, but rather participants in galactic-scale processes that distribute matter, chemical elements, and complex molecules across the entire galaxy through interstellar visitor populations. Every planetary system likely receives regular deliveries of materials from other stellar environments, potentially including organic compounds, water, and even biological materials that could influence the development of life throughout the galaxy. Dr. Amir Siraj at Harvard University studied galactic material transport. Interstellar visitors like 3IATLAs represent a galactic material distribution network that connects all star systems through continuous exchange of objects carrying chemical and possibly biological materials across cosmic distances. The information transport possibilities opened by interstellar visitor populations suggest that matter can carry information about stellar processes, planetary formation, and even biological development across galactic distances, essentially creating a cosmic communication network that operates through physical object transport. Objects like 3I Atlas carry chemical signatures that preserve information about the stellar environments and planetary systems where they formed, delivering direct samples of distant cosmic processes that would otherwise be impossible to study. The panspermia implications for biological distribution suggest that life might spread throughout the galaxy through interstellar visitor populations that can transport biological materials or even living organisms across the vast distances between star systems. If life can survive the extreme conditions of million-year interstellar journeys, then biological materials could be distributed throughout the galaxy, potentially seeding life in multiple star systems and creating biological connectivity across cosmic scales. Dr. Chandra Wickramasinghe explored biological transport possibilities. If biological materials can survive interstellar transport conditions, then objects like 3I-ATLAs might represent vectors for biological distribution that could spread life throughout the galaxy across geological timescales. The chemical evolution implications involve understanding how materials change during extended interstellar journeys and what these modifications reveal about chemical processes that operate in cosmic environments unlike anything found in individual star systems. Chemical signatures preserved in interstellar visitors provide information about stellar nucleosynthesis, planetary formation processes, and chemical evolution that occurred in stellar environments very different from our solar system. The timeline implications of galactic connectivity suggest that cosmic processes operate on scales that dwarf human temporal perspectives while creating connections between events separated by millions of years and vast distances. The chemical composition observed in 3I Atlas might reflect stellar processes that occurred millions of years ago in star systems hundreds of light years away, creating direct connections between current observations and ancient cosmic events. Dr. Maria Bergman at the Max Planck Institute for Astronomy analyzed temporal connectivity. Interstellar visitors create temporal bridges that connect current astronomical observations with cosmic processes that occurred millions of years ago in distant stellar environments. The technological implications for human space exploration suggest possibilities for interstellar travel and communication that could utilize natural galactic transport processes rather than requiring breakthrough propulsion technologies that exceed current human capabilities. Understanding how natural objects accomplish interstellar travel could guide development of human technologies that achieve similar capabilities through engineering applications of cosmic transport principles. The survival mechanism insights gained from studying interstellar visitors could enable human technology development that creates objects capable of functioning across cosmic timescales and surviving the extreme conditions of interstellar space. Human interstellar exploration might become feasible through technologies that emulate the survival strategies demonstrated by natural interstellar visitors like 3I-ATLAs. Dr. Les Johnson at NASA analyzed technological applications, understanding how objects like 3I Atlas survive interstellar travel could guide development of human technologies that achieve similar survival capabilities for cosmic exploration and communication applications. The SETI implications of routine interstellar visitor populations suggest that advanced civilizations might use natural cosmic transport processes for exploration and communication rather than relying on electromagnetic signals that operate at light speed. Artificial objects designed to appear natural could travel between star systems as part of interstellar visitor populations, providing stealth exploration and communication capabilities that would remain invisible to civilizations that focus on electromagnetic SETI searches. The possibility that some interstellar visitors represent artificial objects rather than natural phenomena transforms the search for extraterrestrial intelligence from listening for radio signals to identifying artificial objects among natural cosmic phenomena. The astrobiology expansion beyond traditional life detection involves recognizing that biological or technological intelligence might be distributed throughout the galaxy through interstellar visitor populations that connect star systems across vast distances. Rather than developing independently in isolated star systems, life and intelligence might represent galactic phenomena that utilize cosmic transport processes to achieve distribution and communication across scales that transcend individual planetary environments. The cosmic perspective implications challenge human-centered assumptions about biological and technological development, suggesting that consciousness and intelligence might represent galactic processes rather than isolated planetary achievements. Human development occurs within galactic contexts that include biological and technological processes, operating across cosmic scales and timescales that dwarf individual planetary evolutionary periods. Dr. Carl Sagan anticipated such perspectives. Recognition that the galaxy operates as a connected system transforms our understanding of biological and technological development from isolated planetary phenomena to participatory processes in galactic-scale evolution. The evolutionary implications suggest that biological and technological development might be influenced by galactic processes that provide information, materials, and possibly even biological inputs that affect the direction and pace of evolutionary change. Interstellar visitor populations could influence biological evolution on multiple worlds simultaneously, creating evolutionary pressures and opportunities that reflect galactic-scale processes rather than purely local environmental conditions. The philosophical implications challenge fundamental assumptions about cosmic isolation and individual significance, replacing loneliness-based worldviews with recognition of participation in galactic-scale processes that connect conscious beings across vast distances. Human consciousness develops within galactic contexts that include information and materials from throughout the cosmic environment, creating connections that transcend the spatial and temporal limitations of individual planetary existence. The responsibility implications expand human ethical frameworks beyond planetary stewardship to include participation in galactic processes that affect biological and technological development across multiple star systems and cosmic timescales. Human activities might influence galactic-scale processes through contributions to interstellar visitor populations, modifications of local space environments, or development of technologies that interact with cosmic transport networks. The future implications for human cosmic development suggest possibilities for participating in galactic connectivity through technologies that utilize natural cosmic transport processes or contribute to galactic-scale material and information distribution. Human civilization could transition from isolated planetary existence to active participation in galactic networks that enable communication and transportation across cosmic scales that seemed impossible according to conventional space travel limitations. Dr. Freeman Dyson explored galactic participation possibilities. Advanced civilizations might achieve galactic connectivity through technologies that utilize natural cosmic processes rather than brute force propulsion systems that exceed energy and materials limitations. Consider what the cosmic implications of 3I Atlas reveal about humanity's place in galactic processes and our potential for participating in cosmic connectivity that spans the entire galaxy. You exist within galactic systems that routinely transport matter and information across vast distances, connecting star systems through processes that operate on cosmic timescales while potentially influencing biological and technological development throughout the galaxy. The successful interstellar journey of 3I Atlas proves that the galaxy supports connectivity processes that enable matter to traverse cosmic distances while maintaining structural integrity and carrying information across space and time. Recognition of galactic connectivity transforms human cosmic perspective from isolated planetary existence to participation in galaxy-spanning processes that connect consciousness and intelligence across distances that seemed impossibly vast according to conventional space travel assumptions. The cosmic implications of this interstellar visitor's successful arrival demonstrate that the universe permits connectivity and communication across galactic scales through natural processes that transcend the limitations that have confined human imagination about cosmic interaction and exploration possibilities. Throughout our exploration of how 3I Atlas arrived from beyond our solar system, we've witnessed one of the most extraordinary voyages ever documented by human science. An epic odyssey that began in violent gravitational events around distant stars, traversed millions of years of cosmic emptiness, and culminated in a precision arrival that provided humanity with our first detailed study of a confirmed interstellar visitor. The journey we've reconstructed reveals the staggering complexity of interstellar travel, from its violent ejection during gravitational catastrophes in some distant stellar system, through navigation across gravitational fields from dozens of star systems. 31DTL has survived radiation bombardment that would sterilize any known biological material and temperature extremes that would shatter most substances, while somehow maintaining structural integrity across timescales that encompass the entire evolutionary history of complex life on Earth. The physics of this achievement challenge our understanding of what's possible in material science and cosmic engineering. The survival mechanisms that enabled 3I-ATLAS to complete its interstellar voyage suggest either natural durability that exceeds known limits or sophisticated protection systems that operate according to principles unknown to human science. The precision navigation that brought it to our solar system at exactly the optimal time and trajectory for human observation defies explanation through conventional orbital mechanics. The detection and analysis of 3I-ATLAS represents humanity's transition from a species that could only imagine interstellar visitors to one capable of detecting, tracking, and studying actual objects that have completed million-year journeys between star systems. The technological achievement of precisely determining its trajectory, analyzing its composition, and understanding its physical properties marks a milestone in human cosmic capability. As you continue your daily life with this new understanding, remember that you're living during a unique moment in cosmic history when humanity first developed the capability to study matter that has traveled between star systems. The chemical composition, structural integrity, and behavioral patterns of 3I Atlas carry information about cosmic processes that operate across the vast emptiness between stars, environments so extreme and alien that they exist nowhere in our local solar system experience. When you look up at the night sky, you're seeing not just distant points of light, but the endpoints and origins of cosmic highways along which objects like 31ATLAS travel continuously. The space between stars, which appears empty from our limited perspective, actually supports transportation networks that connect stellar systems across the galaxy through processes that operate on cosmic timescales. The successful arrival of 3I-ATLAS proves that the galaxy functions as a connected system where matter routinely travels between star systems, carrying information about distant cosmic processes and potentially even biological materials that could influence the development of life throughout galactic space. This connectivity operates through natural processes that transcend the technological limitations that currently confine human space exploration to our local planetary neighborhood. The implications extend far beyond astronomical curiosity. The survival mechanisms demonstrated by 3I Atlas could guide development of human technologies, capable of functioning across cosmic timescales and surviving the extreme conditions necessary for interstellar exploration. Understanding how natural objects accomplish galactic voyaging might enable human participation in cosmic transportation networks that span the entire galaxy. The navigation precision achieved by this interstellar visitor suggests either gravitational dynamics that exceed current theoretical understanding, or guidance systems that operate through principles unknown to human physics. Either possibility opens perspectives on cosmic exploration and communication that transcend conventional assumptions about the limitations of space travel. You are witnessing science at its most exciting frontier, the study of phenomena that bridge the gap between star systems while challenging fundamental assumptions about cosmic isolation and galactic connectivity. The methodologies developed for studying 3IATLAs are revealing cosmic processes that operate across scales of space and time that dwarf human experience. The trajectory reconstruction that traced 3I Atlas backward through millions of years demonstrates humanity's growing capability to understand cosmic processes that span geological timescales while connecting events separated by vast distances. We can now chart the course of objects that have witnessed cosmic evolution across multiple stellar neighborhoods. The chemical analysis revealing information about stellar nucleosynthesis and planetary formation in distant star systems proves that interstellar visitors carry direct samples of cosmic processes that would otherwise remain forever beyond human study. Each such object represents a cosmic messenger that delivers information about galactic processes to civilizations, capable of recognizing their significance. The recognition that millions or billions of similar objects might pass through our solar system continuously transforms our understanding of cosmic environment from isolated planetary oasis to active participant in galactic-scale transportation and communication, networks that connect all star systems through continuous material exchange. The panspermia implications suggest that life itself might utilize these cosmic transportation networks, spreading biological materials throughout the galaxy and potentially connecting the development of consciousness across multiple star systems through processes that operate on cosmic rather than planetary scales. The SETI implications of routine interstellar visitor populations suggest that advanced civilizations might achieve galactic communication through physical object transport rather than electromagnetic signals, utilizing natural cosmic processes for exploration and information exchange across distances that seemed impossible according to conventional space travel assumptions. If you found this exploration of cosmic voyaging compelling, please subscribe and give this video a thumbs up. Check out my analysis of the mysterious properties that make 3I they so anomalous. The connections between its impossible characteristics and its epic journey might be more significant than we ever imagined. The successful interstellar voyage of 3I Atlas represents more than an astronomical achievement. It demonstrates that the universe permits connectivity and communication across galactic scales through processes that enable matter to maintain functionality while traversing cosmic distances and timescales that challenge human comprehension. The epic journey we've reconstructed proves that consciousness like yours exists within galactic systems that routinely transport matter and information across vast distances, connecting stellar environments through cosmic processes that operate across millions of years while potentially influencing the development of life and intelligence throughout galactic space. The arrival of this cosmic traveler from beyond our solar system delivers the most profound message possible about cosmic reality. The galaxy operates as a connected, dynamic system where matter can travel between star systems while carrying information about distant cosmic processes, proving that consciousness developing anywhere in the galaxy participates in galactic-scale networks that transcend the isolation that has limited human imagination about cosmic exploration and communication possibilities.